Thank you, Susan, for that presentation. Certainly another tedious issue on really, like you mentioned, day-to-day nuts and bolts, real-world things that we have to deal with. Our next presenter is Michael Smiarowski. He's a senior manager in the steam product line with Siemens, and he's going to talk to us about heat rate improvement opportunities and as they relate to the new 111D Building Block 1 options.
Thank you. Okay, thank you, Steve. Also, with my talk going through my presentation, I'll ask my subject matter expert, Steve Leibrand, to talk about the other aspect of our heat rate improvement potential here at coal-fired plants as we go through a little bit. So my colleague also from local Alpharetta facility here outside of Atlanta will also be speaking. But we'll talk a little bit about solutions for coal-fired plants here to comply with the 111D, specifically the 6% heat rate improvement. And as a preamble, I know Steve Leibrand and I, we were called into our executive sales manager's office a couple of years ago now in preparation for these rules, and our sales executive said, hey, our customers are asking what can we do to improve heat rate at your plants? And we had a number of product lines represented, but it really came down to the steam turbine and the process control here areas that were able to give, I think, the most immediate bang for the buck, and we had products ready to go. And we've been talking about what we can do for solutions ever since here, kind of tailoring our message to that. So we'll be talking about that a little bit this morning. Well, it still is morning. I'll be covering these topics here, a little bit of Siemens background, as I mentioned, heat rate reduction, and some solutions. And then I'll let Steve talk about his process and wrap up. A little bit about Siemens. You know, I was the sucker for the marketing TV channel here at the hotel. It said, if you happen to go to a German restaurant close by, Der Biergarten. I dragged a couple of guys from the conference. We went there yesterday, and it's a German restaurant. I tried to ask the waitress if she knew anything about Germany and whatnot. And I said, do you know what the biggest European-based engineering company in the world is? And she gave me a blank stare. And then I said, this is a German-based multinational. And I pointed to my shirt, maybe thinking she may get it. And then she said, Lufthansa, so didn't get the right answer, but Siemens, we're involved in a number of different sectors: healthcare, industry, energy, and also infrastructure in cities. And then in our specific sector in energy, you can see we're all for renewables. We do a great business with wind power, combined cycle plants, their transmission and distribution, and then our more traditional power plant equipment and services. And that's what I work in the service area, where we're trying to improve and keep the existing assets viable into the future. Just a topic on here in the United States. Globally, Siemens has about 360,000 employees, and our latest numbers here from last year here in the States, we have about 46,000 employees involved in Siemens' different product lines, and doing about $22 billion in business. So we've got a big chunk of our employee base as well as our revenue coming here from the States. And one last kind of drilling down into our topic, where our facilities are. I'm from the Orlando headquarters. The speaker before me was from Pensacola, so I'm going back to Florida here tonight. But we have our main facility here that manufactures gas turbines, steam turbines, generators, and does services in Charlotte, North Carolina. And then in our steam turbine operations, you can see our global capacity includes facilities in Germany, Erlangen and Mülheim, Germany, as well as Newcastle, England. And then a little bit more detail on our North American facility, the Charlotte facility, some of the statistics. We really invested in that facility the last few years, doubling the capacity about 3 years ago. And you can see some of the statistics. It has about 1,600 people working there on a wide range of products here. And just to show you the collage of different products and services that are sourced from Charlotte, this gives you a representation. So really a world-class facility that supports what we're trying to do for the power industry here. So to kind of move on to the topic, we talked about the EPA 111D, the building blocks, and I got from actually Steve's earlier talk that the last increased demand side efficiency building block has gone away. We've really focused our attention, Steve Library and myself, on the first one, the heat rate improvement area for coal-fired plants, getting that targeted 6%. And we had to draw on a couple of examples here. Mainly, about 2 years ago, we drew from a European example, which I'll talk about, and then we have some more closer to home examples doing a steam turbine modernization project for the coal-fired fleet. And the units that we're focused on are these aging units. This graph was from our business development area. They segmented the units here, the aging coal-fired fleet, if they're scrubbed or not, and nameplate capacity and whatnot, and age. And you can see where it's kind of dash circled the newer, larger output units. Those are the ones that will likely be the survivors into the future, and those are the ones that we've been developing and talking to here continually. As part of the EPA Clean Power Plan, they're talking about where coal is going to go in the next few years, and it's not going to be dead, thank goodness. In 2030, the EPA cites about 27% of our generation is still going to be coal-based, so there still is a viable market there, and one that companies and people like myself and my colleagues here will be focusing on and talking to. So that's what we're looking at, and when we look at that 6% heat rate improvement on the steam cycle here of the plant, meaning the main steam turbine, the inlet to the turbine, the valves, you have the generator, condenser. Those are areas where you can certainly optimize, maybe implement some new design changes and things like that. But the proven and most widely done project here to get a good return would be the steam turbine modernization, which is my specific area. And looking at modernizing your steam turbine, which means changing out the turbine itself with new technology. You can look into the various different types of turbines. For those of you who don't know turbines, you have the high-pressure turbine, a combined casing HPIP, intermediate pressure turbine, low-pressure turbine, and then other areas talked about like the valves and condensers also have potential for heat rate improvement, but those are a little bit more subjective project to project. But the ranges of improvements from a baseline conditions technology only have been in these areas. So when we're talking about 6%, you can see doing a turbine upgrade, you're going to get a good portion of that. And in prior years, the bang for the buck has always been in the HP turbine or the HPIP turbine. You can see you have up to a 3% improvement, and you get yourself halfway there. Those were type of projects that we've had a great business on over the last decade for the payback, for the return on investment of equipment that's essentially at the end of its design life. Now, when you move down further, when you're trying to make a business case for like intermediate pressure turbines or low pressure turbines, it's a little bit more difficult. You don't have the immediate return on or as high a return on investment and the quicker payback. Normally you need other drivers like reliability to support that type of business decision. But this gives you a good idea here of the different turbine components and what they can produce in the heat rate improvement if you implement the new technology. And the new technology, for those of you who aren't turbine experts, really is broken down into getting more work out of the steam. What you do there is you improve your interstage sealing. You apply latest design blades. All turbine manufacturers have some series of three-dimensional type of blades in the shorter length applications. You have more technology advanced profiles that are able to be designed nowadays due to computer-aided manufacturing and design. And then getting into the low-pressure turbines, if those are being replaced, you have your shape of those low-pressure sections as well as the length of those, which also add to your performance improvement. So to give you a little bit idea here, this slide's showing closest to me here, the 3D blade here, the picture. You can see the radical shape there is our latest design. Again, being able to be manufactured due to advanced milling machines, literally 4-axis milling machines to do that, which you couldn't do, let's say, over 10 years ago. The interstage sealing showing up in the top there. So literally there you would do a different type of configuration or add maybe more seals to direct more steam through your steam path and get more work out of your blade path. Here talking about the low pressure blades, this also the picture closest to me here is a long freestanding blade, so that design, the twist design is also a feature that over the last 15 to 20 years has aided in better performance, and it has a lot of the same design features and modeling features that are able to get to a more efficient product here in the blade technology. So pretty mature technologies that we've implemented over the past years. Getting back to the sealing here, you have a little bit, you had some diagrams of seals earlier. Here are some advanced sealing concepts that we use on a selective basis here. If you're really trying to get every last bit of work out of the steam, some of the features here are retractable brush seals, abradable coating seals, and retractable seals. All of the concepts there are to facilitate the tightest possible clearance to your rotating element. And in the case of, like, let's say a brush seal or an abradable seal, you actually have zero contact there on those particular sealing technologies, and your retractable seals actually close up clearances in operation. So those are the type of things that are those tweaks in the turbine that get you the better performance out of the steam. When you put all that together and you try to get a project here that gets us to where we want to go, the most efficient type of design and payback and whatever the customer drivers are, you can get some good results here. And this reference plant was actually in Germany. They published their results back in about 2012. You can see this Ibn Buren plant, 750 megawatt plant. Some of the key criteria of that particular project, they did achieve over 6% heat rate improvement, but this came as a major project where they changed out every turbine element, the 4 turbine elements on the top here with new technology, and they also optimized the condenser as well, meaning changing the arrangement of the condenser tubes to facilitate better flow and heat transfer. So all those things you can imagine is a very expensive project, but you can see the results there, the 6% heat rate improvement, what they cited as 86 megawatts total improvement of the project, which half of those were due to technology megawatts, because they did raise some of the steam conditions as well, which I'm going to just show here very quickly, that customer went through a very rigorous process doing an assessment of their existing plant, getting input from not only Siemens but also the boiler side. They raised their live steam temperatures and reheat temperatures a little bit here, and the mass flow increased, as well as some of the other criteria So a lot of engineering went in the front end before they actually did a cost-benefit analysis and proceeded with this project, which was really an integrated total plant solution for Siemens and this customer, which is RWE. So you can imagine this is a coal plant in Germany, which kind of goes against the grain. But talking about market drivers here, Germany probably pays about 3 times or 4 times as much for electricity per kilowatt hour than we do, and they don't have the abundant gas. So coal is their cheap fuel still, if they can get around a lot of the pollution legislation and whatnot. And they have a lot of renewables, which has turned their market upside down. But you can see this is one of their surviving coal plants that really made a significant investment. Getting a little bit closer to home, just earlier this year, we were involved in a project in Missouri at the Asbury plant. You can see this was a small utility, Empire District Electric Company. They made a conscientious decision to continue operating the plant. They started in 2012 with installing their back-end cleanup equipment, the scrubbers, baghouse, carbon injection. They contracted with us for replacement turbines, which we installed starting last fall, so a little bit over a year ago. They completed the turbine outage in about 40 days. They tied in all the pollution controls earlier this year in March, and then the performance testing was done also earlier this year, and all our guarantees were met. There were additional heat rate tests that were done that due to confidentiality I couldn't publish here, but they also got pretty close to 5% heat rate reduction in this type of project with the turbines. So a very viable project, and you can see the picture there is the BB145 turbine being installed at the site, the nice new shiny turbine going in. And this gives you just a kind of a comparison of the old technology and the new technology, how it's evolved a little bit. The lower half shows the original equipment. So called out in the numbers are the individual components here. So you have 9 different components in the lower half that are subject to steam forces that have to be installed, aligned, can warp over time, etc. What's interesting is the steam admission area. I know this is maybe a little bit difficult to see right here. On the old design, it actually goes towards the middle of the unit, contrasting with the new design where it actually goes outboard from the center and through the steam path. So all these little design changes improve the efficiency, improve the maintainability of the design and of the equipment going forward. So that's kind of a comparison of the old 9 components to 3 major components with the new equipment that we provided earlier this year. Just kind of showing a little technology on the low pressure turbine. We follow the same technology approach. We want to change everything inside your exhaust casing, so the steam path again, with all new equipment here. So with that type of approach, you have some flexibility to add more blade stages in this axial section, have longer blades as well, as I mentioned earlier, and that all translates into better performance over time. And this kind of gives you an idea of some of the sealing arrangements that are done here to guide the steam through the blade path and get more work out of the steam here in the low pressure section. So that kind of gives you an idea, a little bit of our technology. Here's some nice photos of the new equipment. This is showing the low pressure turbine for the Asbury plant. This is actually in our factory in Germany here, being final aligned with a boring bar prior to acceptance and shipping to the site here. So you can see some of the things you'd see in our factory. Oh, I'm sorry, I jumped ahead. And here's the rotating element we call the rotor, also ready to go with all the blades installed at the factory as well. And a little close-up of our rotors as it's being finished up. So gives you a little impression of some of our equipment that can be implemented today at our surviving coal plants that they can get that type of heat rate improvement here. But of course, a significant investment. It has to be a plant that's obviously a survivor, that's going to be called into service quite a bit over time. So that's my steam turbine section. I'll turn it over to my colleague, Steve Librand, to talk about the process improvement potential.
Let me figure out this, which is the button to go. Just right. Okay. Well, good morning. I'm based in Alpharetta, just north of Atlanta. Been in this business for quite a long time. What I'll be talking about today is fundamentally the drivers that we are seeing from a controls perspective. The part of my work in is not only instrumentation, but also electrical. The drivers that we see you facing fundamentally are listed here. Heat rate has always been an issue. That's nothing new. The difference is that you've been focusing on heat rate at the top end with coal-fired units. You've never been focusing on, well, hardly ever, been focusing on heat rate down at the bottom end. Now, your units are going to be moved around quite a bit, and the amount of time you spent at the minimum load is going to increase. So that's the slight difference there. I'm not quite sure how EPA reviews that. You know, I know, heat rate goes up. When you're going down, it gets worse. When you're at low load, what that does to emissions is make it worse. So this heat rate improvement is very important, but as you change the requirements, the operator requirements on a coal-fired unit, we may see the reverse actually happening on emissions. We also see a requirement to redispatch to other energy sources. We don't need to talk about that, it's well known. Flexibility, maneuverability, that has never been a big, important criteria for coal-fired units. When I looked at coal-fired units, when I started in the United States in 1998, you couldn't sell a load ramp, a fast load ramp for any amount of money in the world, even zero and minus, give it away. Today, that's becoming more and more important. And flexibility, maneuverability, that doesn't, as you know, doesn't cover just load ramps. It also covers down the minimum load. It used to be a startup is also part of it as well. What was a bigger driver in the past was increasing capacity in any way you could possibly could. On coal-fired units, if we look at other countries, the performance in other countries, Siemens is a global country, so we have references. I particularly have reference and relationships to the other colleagues around the world, and I see what other coal-fired units have to do around the world, and some coal-fired units have been a lot more pressure than us, and going forward we'll catch up with them pretty quick. Particularly Germany have had to make their coal-fired units extremely maneuverable. They actually cycle their plants on and off on a daily basis as well, not the whole year round, but when they're in service. That has never been a consideration for us, but maybe we should start looking at that. Right now, we're getting, we'll talk about it a little bit later, we're getting requirements for coal starts and coal-fired units, but cycling coal-fired units right off and back on again on a daily basis, not really a requirement. What was interesting is the previous discussion as well about the startup requirements. We're finding that even though the title of the subject title is coal-fired plants, we're finding that because of the requirements in the coal-fired units, the combined cycle plants, gas-fired cycle plants are also being affected, but in the reverse direction in some cases. Interestingly enough, I find that there's a lot more interest now in increasing the load ramps of combined cycle plants, and which was a little bit unexpected, but certainly that I see that today. What's interesting to say about that is this. As you requested from us, faster load ramps on combined cycle plants, we started to look at it a little bit more closely. And as the OEM, we can actually look at the root cause of the limits that we've put on the machines. And for example, some of the machines, we have 13.5 megawatts a minute as the limit. But the actual limit is not the megawatts. It's actually the differential expansion of the blades and the casing. And make sure you have those clearances. So if you look at that a little bit more closely, all of a sudden you find during the startup, there's a specific limit you have to take care of. but during minimum load and maximum load, all of a sudden, the 13.5 doesn't make sense anymore, and that you can utilize a lot more, you can go a lot faster. Now, that's where software can actually play a role. And the software is programmable, as you know, but also can calculate complex situations. In other words, we don't calculate the actual the clearances. That's complexity that's probably a little bit too high for the current DCSs, but you can actually calculate limits. If you look at the firing temperatures, you can actually calculate the rate limits from that. So in other words, all of a sudden your 13.5 from minimum load to maximum load becomes 30 megawatts a minute without impacting the clearances. So that's something that we can look at from a controls perspective to meet the requirement for flexibility and maneuverability. This week, for example, at one power plant in ERCOT, we're looking at heat rate improvements, combustion optimization, and the plant that we also visited at the same time, the next plant, was looking at flexibility, maneuverability. And that was an interesting discussion. Fundamentally, they were looking at load ramps and minimum load reduction. Big coal-fired unit. Now, what was interesting from that discussion was when I asked the question, what is the value of a load ramp to you? We were talking to the plant personnel. They were not sure of that. So what I'm seeing is when I talk about market drivers, that's a misnomer. It's regulation drivers right now. It's just regulation and penalties. There's no real market incentives for the plants themselves to do stuff. Now, it was an edict from the head office that said, you guys have to improve your load ramp rates, you guys have to reduce your minimum load. Now, when we asked, well, okay, what minimum load you're targeting? And they basically said, head office like 0. No, 0 means you cycle off. So fundamentally, when we looked at what they were facing, we were looking at hard stops. We were looking at the flue gas temperature minimum for the scrubbers and equipment on the back end. We're looking at vibration on the turbine. So there's hard stops to minimum load reduction. We can do a lot with controls, increased stability, things like that. But those hard stops require significant investment. So when we look at the head office, you could say, and the plants themselves, there seems to be a slight discrepancy about what is achievable and what can be done. And also we're seeing that the incentive side of this whole issue that we're dealing with right now seems to be lacking a little bit, but I'm sure as we go forward, we'll see more incentives. The other aspects, we just continue down the left-hand side just briefly. Convert startup and shutdown to gas. I read that in Matt's myself. I may have misinterpreted, but it seems to me there's a lot of positive if you do convert your startup firing to clean fuel, as it were, but also expand the capacity. All of a sudden, your minimum load reduction possibilities increase. So, in other words, when you're bleeding money overnight, where you're getting not paid for very lot, and you're spending a lot for generation, all of that sudden, the minimum load reduction becomes more viable if you just look at that requirement as well. So what I'll be talking about today is process optimization, looking at heat rate emissions, maneuverability, and startup. As I said, at full load, you have pretty much that well in grasp, but at partial load, there can be still a lot to be done. This is a typical sort of roadmap we have for partial load efficiency improvements. One of the things not shown on here is the flexibility and maneuverability, and you have to achieve both goals at the same time. So even though you're doing these sort of things, you're using these features here, the maneuverability should not be impacted. So if we take a look on the left-hand side, we're looking at the combustion optimization, which is just fuel-air ratios, fuel-air staging of the combustion. This has been around for quite a while. We have solutions. We use, in particular, the furnace temperature, or the temperature profile, the O2 profile, CO profile in the furnace just above the burners. That gives us immediate feedback on the products of combustion and allows us to adjust accordingly. The important point here, as all of you know that are from power plants, that you're firing at minimum load, is not going to be balanced simply because of the burner configurations that you have when you go down low. That you can have a really well-balanced fire-centered and T-fired units, centered fireball, all of that at maximum load. But once you start going down at lower loads, all of a sudden the availability of the burners you can use for the configuration make the combustion a little bit imbalanced. And that's where these furnace measurements can actually get you back as balanced as far as possible. We have the intelligent soot blowing solutions. They've been around for quite a while. They work in conjunction with the other optimization solutions, and obviously these have to work even though increasing the load ramps and reducing the minimum load. We have the steam temperature control optimizers as well. We have the dynamic sliding pressure. Sliding pressure gives you better heat rate at the lower loads. But what's important about the dynamic sliding pressure is for coal-fired units, is we decouple the pressure set point from the load set point time-wise, temporary in time. So in other words, you're not overfiring for both at the same time or underfiring, whichever way you're going. So in other words, it's a much smoother operation. You get the benefits of the efficiency improvement, plus also you get the benefits of the heat rate. On the right-hand side, we got IPLP, steam extraction manipulation. That's another thing that we don't use in the United States. That is the energy sources in the steam-fired power plant itself. There's a lot of energy sources we don't utilize. In fact, the controls primarily fight against them. The types of energy sources I'm thinking of, for example, is the volumetric steam, the volume of the boiler, the steam volume. Not only that, there's the thermal energy in the metallic parts of the metal parts of the boiler as well. These are all sources we can use in our strategies for maneuverability in particular. And one of them is the energy of the condensate and feedwater systems. We can actually utilize those sources of energy to bridge the delays in the coal firing. The firing delays, everybody knows that in coal, it's much longer than in gas, for example. So while you're bridging those delays for faster load ramps and maneuverability, you utilize the energy storage to do that. We have the back-end optimization as well that Mike already talked about. One of the things I see, a lot of power plants are well down the path of looking at variable speed drives for the fans and pumps for large motors. Particularly important once you start moving your load down to the bottom end. In other words, increasing your turn down ratio. You'll find that a lot more important. So the bottom line is here, you want to increase the heat rate, or improve the heat rates, but you don't want to impact or reduce your maneuverability. You want to increase the maneuverability. One of the things that I see coming up a lot more is improved cold starts. We found that a typical cold start for a coal-fired unit could be anywhere between 20 and 30 hours, roughly. And with judicial looking at the procedures, not just controls, but getting equipment ready in time for the call to start up without using auxiliary power by keeping large machines or large pumps, large fans in service, just getting ready to go, you can actually reduce that to less than 14 hours. In some markets, that's being now rewarded. But that's something that you can look at, and as I say, I call them colleagues around the world, they're already cycling off completely on a daily basis, coal-fired units. So anyway, there seems to be a large interest, more interest in coal startups reduced less than 14 hours. Operating flexibility, as we've already talked about, faster load ramps. Generally speaking, you look at doubling up the load ramps. Currently, around the world, I see coal-fired units, in particular Israel, they do 10% per minute. Same equipment that you have, drum boilers built by CE, 10% per minute, close to set point, load ramps, it's possible. Cold starts, as I mentioned already, fast starts, what we do as well, and just like to say that we also do that for combined cycle plants. But fast startups, 20% to 70% fuel reduction. We've done that already. We have references for that. Lower minimum load. There are hard stops here that may require investment in mechanical equipment or plant configuration changes on the fly. But going forward, at least from a turbine perspective, that's where you can get down. The boiler, there may be boiler limitations as well. If it's related to controls, we can actually fix that as well. This is what we have achieved on units around the country. Just to conclude, Mike's speech and mine, the 6% heat rate, which was always regarded up to now, has not been possible. It's just a pipe dream, can't be done. We've seen it can be done. The investment is significant, but it can be done. The combination of it's listed as steam turbine process optimization. What it is, optimizing the steam turbine plus the boiler and the boiler components, you can achieve this target. The other conclusion, we talked about coal-fired units, gas-fired steam plants, nuclear upgrades, in particular for the steam turbines. Definitely large improvements can be seen there. And as I mentioned on and off, also for combined cycle plant as well. Thank you very much.
We have time for a question or two if anybody has a question. No questions?
Michael, in your chart showing the sections of the turbine that you might expect heat rate improvements from, that chart has a lower limit, seems to be sliding scale on the lower side, but it stops at 6% on the upper side. Does that imply that typically those improvements will total less than 6%?
Yeah, I believe the chart, I was trying to show individual components. Let's say the high-pressure turbine, combined HP, IP, and LPs, and then we had valves, condensers. The intent of that slide was to show the approximate range if you changed out that one element. When you start doing an entire steam train, multiple elements like the Ibn Buren did the whole turbine train, Asbury did the whole turbine train. You usually get additive, combined heat rates, and you get up to that higher level. Let's say the 5 or 6%. Individual components like the intermediate pressure turbine or low pressure turbines, you just don't get the bang for the buck. The heat rate improvement, no matter the technology we apply today. It's just it hasn't. The LP turbines and IP turbines don't do as much work as the high pressure or the combined casing HP IP. That's kind of like the reason for that. But really, each row was meant to show essentially the range of
it looks like that upper range is 6%. Is that it?
If you do the whole, yes. If you did the whole thing, that's what we've had references here that have achieved that. We haven't had a customer in let's say the last few years that has done everything and has gotten 7%. And bear in mind that doesn't include let's say aged equipment that already is deteriorated. We're trying to account there for a technology change. So your old technology from 30 years ago in the as-new condition, comparing it to the new technology being installed today. So you could actually achieve changing out the turbine more than 5 or 6% easily. Okay. Oh, there's some more questions.
You answered one question, which was in regards to whether that was looking at new versus worn conditions. But the other question is how do those percentages change much when you look at dispatchability issues and things like that?
Well, we touched on that a little bit here on Steve's discussion. These old, the coal fleet no longer is running in base load capability, right? They're low turn down. You had a slide actually. One of your slides went down to 8%. I think is some of the lower turn down. As you go down in load, your heat rate's going to go up, which was talked about quite a bit. The ranges we were talking about citing here would be the as tested conditions, valves wide open condition as part of our performance verification testing. You have to have a design point somewhere, and that's kind of where we set our basis for that discussion in those values.
I had a question concerning the converting to gas for the startup and shutdown of how you're actually improving efficiency, because converting to gas, you're going to have higher moisture losses.
Steve, was that?
Would you repeat the question again, please? I didn't quite hear it.
You had up on the slide there that to have a efficiency increase, that you would convert to gas for startup and shutdown. And my question is, how's that giving you an efficiency increase when gas itself has higher moisture losses in a boiler?
The slide that you're referring to just basically said, sort of looked at the market trends that we observed from the controls perspective, and I think there were six bullets right up front. One of them was what we expect to see on coal-fired units, maybe to convert to gas. Now we've seen that gas firing. Now we've seen that since decades. I mean, the first one we looked at was Grand Tower, and that's about 15 years ago. So that's been in process for a while. Now, the question I understood was something about the efficiency maybe decreasing if you go to gas. The objective, as I understand it from a controls perspective, the objective is to reduce greenhouse gases. And if you look at the production of greenhouse gas from gas overall, as opposed to coal, you find that natural gas produces a hell of a lot less just from the natural combustion process, irrespective of the cycle.
But I thought the rule is about energy efficiency. It's not about emissions. It was about energy efficiency that would translate into emissions.
He thought switching to gas would be, we were trying to imply that it's more efficient. I don't think
No, not at all. No, I wasn't talking about the efficiency at all in that particular bullet. That bullet is just purely with respect to production of greenhouse gases. That's what we're looking at right now. Now, as far as the efficiency of producing power, the efficiency of the cycle, actually, I haven't looked at it. All I know is that those Rankine cycle units, they're usually about 30%. And switching to gas, I'm not sure that would improve that at all. So that particular bullet was specific in production of greenhouse gases. If you change to gas, it would go down, not megawatt efficiency production. I don't know if that addresses your question, but that's how I understood the question.
Well, my comment isn't the rule about energy efficiency, because I could reduce emissions by going to gas 100%, and there are other options if all I had to get was a 6% improvement in my emissions. But I thought they were talking about energy improvement.
I don't know. I guess I think we're getting something confused here.
Yeah, actually, if you could just talk just a little bit louder. I'm 63. My hearing is not good.
My question is, it's not the rule about energy efficiency and a 6% reduction in your energy consumption. If it was about emissions, we could do something else to reduce the emissions by more than 6%.
Yes, no, we're talking about two different things. If you're talking about the heat rate of 6%, which was the subject of Mike's discussion and a large part of my discussion, yes, we are looking at trying to get heat rate improvements. That particular bullet has nothing to do with the 6%. As far as I understand, Mike also showed a diagram with the four different aspects of the Clean Power Plan. One of them is the 6% heat rate. One of them is to dispatch to renewables, and also to dispatch to other types of firing, for example, gas firing unit. And the fourth, which Mike said has gone away, which I wasn't aware of, that's the demand efficiency improvement. Now, if you look at the other aspects, not the 6%, the redispatch away from coal to other sources of energy in an effort to reduce greenhouse gases, that's one of the things you could look at. In other words, to get not the 6% block, but one of the redispatch to other types of firing, that particular block. That may be something that states overall would consider, but that's not part of the 6% heat rate that we were discussing up to now, if I've misunderstood it again.
Okay.